We're live.
All right, okay. Good afternoon, everybody. Welcome to video lecture number 2. As you all know, class has been canceled again due to the hazardous smoke outside. Hopefully all of you guys are inside reading ventilated air, not outside air, since it's pretty awful. Today's lecture was going to be a review lecture for the midterm. The midterm is still slated to be given out on Monday of next week. If they cancel class on Monday, then we'll figure it out when it gets to that point. Hopefully it doesn't. Hopefully the conditions outside get better. So today we're gonna have a review lecture just like I did for the first midterm. I have a bunch of examples we're gonna work through. The good news is because this is a video lecture, I have an unlimited amount of time, so I can go through all the examples. So you guys don't have to like pre-select them. I'm just going to go in order from example 1 to 15. I have 15 examples. The exam is going to go over only these topics. So it's going to be gases and pressures, gas laws, ideal gas laws, law of combining volumes, gas stoichiometry, Dalton's law, the kinetic theory of gases, Graham's law, and diffusion. So this would be chapter 5 in your textbook. Then in chapter 12, we're going to go over atomic spectra, the Bohr atom and energy state changes, wavelength calculations, sorry. The energy of a photon, where it's E equals h nu or E is equal to hc over lambda, de Broglie and the uncertainty principle, particle in a box, probability density, finding nodes for atomic orbitals and drawing atomic orbitals, quantum numbers, and finally multi-electron atoms and electron configurations. So this is all that's going to be in the exam. I will be very clear, periodic trends will not be on the exam. So the later half of Wednesday's lecture that I covered over video as well, that had periodic trends, electronegativity, ionization energy, that will not be on the exam, so you don't have to study that. Okay, so that looks like it's behaving. The projector was turning on and off on us earlier. Okay. So, okay, you see that?
Yep.
All right. The last column is filled with mercury and inverted in a pool of mercury. The mercury column stabilizes at a height of 735 millimeters above the pool of mercury. What is the pressure of the external atmosphere with atmospheres? So this is a barometer that this example is describing. So I'm going to draw a rudimentary barometer. This. So we have an inverted column that's filled with mercury. Here. So this is filled with mercury liquid. And it stabilizes at a height of 735 millimeters. So as you recall, 760, let's do it like this, 760 millimeters of mercury is also equal to 760 torr, which is also equal to 1 atmosphere. So this is just a simple conversion. We're going to convert 735 millimeters of our column to just atmospheres. So we're just going to do a simple dimensional analysis going from millimeters of mercury to atmospheres of the pressure that's being exerted on this pool. So we have 735 millimeters of mercury. This, for every 1 atmosphere, we have 760 millimeters. So in atmospheres, we have 0.967 is going to be the atmospheric pressure that this barometer is experiencing. So this is just a basic dimensional analysis question. So that's example 1. And we can move along because you guys can pause videos and go backwards, watch it at 2 times speed, make me sound like a bee. Watch it at quarter speed, make it sound like a I don't know if YouTube has tours. I think it does. I'm not sure. Get another plastic sheet. Example 2. Switch this up a little bit so that I get a reflection. All right. 3 1-liter flasks at 25 degrees Celsius and 725 torr contain the gases methane, flask A, carbon dioxide, flask B, and ethane, C2H6, flask C. In which flask is there 0.039 moles of gas? So I'm going to use the ideal gas law for this. So the first thing I'm going to want to do is I need to convert my units to the proper units that you can use in the ideal gas law. I have to convert my degrees Celsius to Kelvin. I have to convert my pressure, which is in torr, to atmospheres. So let's do the torr first. 725 torr. 1 atmosphere, you have 760 torr. So this is simply the conversion we did in the previous example. This comes out to 0.954 atmospheres. Now I'm going to convert my degrees Celsius to Kelvin. So that's just going to be 25 degrees Celsius plus 273.15 gives me 298.15 Kelvin. Just love the cancer in the air, man. Sorry. Okay, so we're going to use the ideal gas law. We have PV equals nRT. I'm going to rearrange this equation so I'm solving for n. So n is going to be equal to PV over RT. And we have all the variables in this equation we have units for. We know what the pressure is, we have 0.954. Volume is going to be 1 liter, because they're all identical. And temperature is 298.15, and R is our gas constant, which is 0.08206, not 8.314. Remember, when you're doing ideal gas law with the old standard, where our pressure is in atmospheres, you use 0.08206. So N is going to be equal to 0.954 atmospheres. Volume is 1 liter. And this is going to be for, we're doing this for flask, let's do it for flask A. And you'll see when we get to the answer of this that there's a trick going on here. This is kind of a, makes you think about the equation. 0.08206, so liter atmospheres per Kelvin per mole. And our temperature is 298.15. Number of moles for this is going to come out to 0.039, which is exactly what the question was asking. It said, which one of these flasks is 0.039? Well, the ideal gas law considers the moles for all these containers the same. So none of these containers have a different value of 0.039. You'll notice that there is no molecular mass in this equation. You're not solving for molecular mass, so you don't have to worry about the mass for these individual molecules. So the number of molecules of methane in flask A is equal to also the number of molecules in flask B, which is also equal to the molecules in flask C, given these conditions. So at this temperature, at this pressure, and at this volume, you will have the same number of moles. So this is all have 0.039 moles inside of their flasks. You could have done this question without doing the math, just looked at it and seen, well, they all have the same volume, they all have the same pressure and temperature, so obviously they all have to have the same number of moles, based on the ideal gas law. If you were, no matter which way you look at it, it'll give you the same number. Makes you think about gas properties, how they behave. Okay. That's example 2. 3. Body temperature is about 308 Kelvin. On a cold day, such as what volume of air at 273 Kelvin must a person with a lung capacity of 2 liters breathe in to fill the lungs? So your lungs are pretty cool in that the pressure inside of your lungs has to be constant. If it's not constant, you're going to get some weird issues, man. So given the temperature outside, your body will adapt itself so that the pressure that you feel inside your lungs is constant. Of course, if you're in space, that's going to be a different issue. If you're just out there in space where there's vacuum and you're not in a suit, then pressure in here is going to be lower than the pressure outside. And well, yeah, you've seen the movies where people bleed out their orifices. It's pretty bad. So for this person, our number of moles and our pressure is going to be constant. Oops, can't draw an arrow. This is a law that we learned in class. This is Charles' law. So this is kind of the law of combining, not combining volumes, but of doing two separate ideal gas law equations at the same time, where our number of moles and our pressure is going to be constant. So if we were to write our equation for the ideal gas law for one condition and the ideal gas law for another condition, it all boils down to V1 over T1 is equal to V2 over T2. And you know that V1 is going to be equal to 2 liters. T1, we're going to set that to 308 Kelvin. And our T2 is going to be our colder condition. So we want to know what volume does your lung have to be to keep these two constant when you take a breath of that cold air. So we're going to plug in our values. So V1 is 2 liters. T1 is 308 Kelvin, equal to V2, which is what we're looking for. So this is our variable. And our colder day is 273 Kelvin. So I'm going to rearrange this. So I'm going to move this T2 temperature to this side of the equation so I can solve for V2. 2 liters over 308 Kelvin times 273, because we have to multiply by both sides to move it over here. Our V2 comes out to 1.77 liters. You'll notice that as the temperature went down, volume went down, which is what this relationship tells us. Okay, so that was example 3. Of note, at the very bottom of these questions, I put the topics that are related to the question. So this question involves Charles' law, empirical gas law, gases, general chemistry, and phases. It's just what I did to. So if you are not good, if you don't understand the mechanics of this question, then you can look this up in your book and read about it and become an expert, and then return the example, and then you'll really understand it. That was example 3. Just give me a bit of a conceptual question here. A cylinder is fitted with a movable piston. The pressure inside the cylinder is P sub I for initial pressure, and the volume is V sub I, initial volume. What is the new pressure in the system when the piston decreases the volume of the cylinder by half? So we have a piston. Let's say we have this container with a piston that can move up and down. There's a initial pressure of this container and initial volume, and this piston is going to move down, and it's going to decrease the volume of this by half. And it wants to know what's going to happen to our pressure. What is the new pressure? So we have to consider the number of moles. There's no gas leaving or entering this container, so our number of moles are going to be constant. And our temperature is going to be constant. So this is a Boyle's law. See if I can scooch it in right here. Boyle's law. I'm going to use a different pen. Let's kill this one. So let's use green. So for Boyle's law, our P1 V1 is equal to P2 V2, where this is going to be our initial pressure, so I'm just going to change our P1 to I, our VI is V1, and P2, we're going to call this P final. And we know that our final volume is going to be half of the initial. So what I can do is, instead of writing V2 here, I'm going to rewrite this as VI over 2, because we're decreasing it by half. So all I'm going to do is I'm going to rearrange this equation so I'm solving for P sub F, our final pressure. So I'm going to move this part of the expression to the left side by multiplying by 2, so the 2 goes over here, and dividing by V sub I, so the V sub I goes over here. So we're going to have 2 over V sub I times P sub I, and V sub I is equal to P sub F. And our V sub i's will cancel out. It's just math, because you're dividing V sub I by V sub I, meaning that the pressure in the container is simply just going to be 2 times the initial pressure. And this would be your final answer. Which makes sense. If the temperature is going to remain constant for this, when you decrease the piston, when you move that piston down, you decrease the volume, the pressure has to go up. There's no other way. Okay. So that was example number 4. What time is it now?
12:04.
12:04. Example 5. Mercury vapor contains mercury atoms. What is the volume of 200 grams of mercury vapor at a temperature of 822 Kelvin and half an atmosphere? So this is another ideal gas law equation. So we're going to use the Pippert equation in a second. We want to make sure we have our right units. Right now we have the correct temperature units, we have it in Kelvin, we have the correct pressure, which is in atmospheres, and we have grams. We have 200 grams. So what we're going to do is we want to convert 200 grams of mercury to moles of mercury. So we can do a little bit of stoichiometry right here. Okay. So we have 200 grams of mercury. Every mole of mercury has a molar mass of, I have a periodic right here. I really hope this doesn't turn it off. Mercury, where are you? You're right there. Try now. Oh my God. There it is. Okay. Mercury has a molar mass of 200.59 grams per mole. Sorry, I'm boring you, Dan. Dan's sitting very patiently in the background, just chilling out. He's doing very, very, very good counting. Number of moles are 0.997 moles of mercury. So now what we're going to do is we're going to use our ideal gas law. PV equals nRT. And we're going to solve for volume. So we'll solve for this. So volume is equal to, we're going to divide both sides by pressure, so we get nRT over P. Plug some values in. We just calculated our moles, that's what N is. 0.997 moles. going to squeeze in the ideal gas law here. Sorry, the gas constant. 0.08206 liter atmospheres per Kelvin per mole. And our temperature was 822 Kelvin. Over a pressure of half an atmosphere. So our V is going to be equal to 135 liters. Our moles cancel out here. So if we looked at our units, our moles cancel out here, Kelvin cancels out here, and atmospheres cancels out here, so all we're left with is liters. So the answer is 135 liters. It's always nice to double check your units, because if you end up with units that you shouldn't have in a final answer, like if you solve for this and your final unit was in moles and it's asking for volume, you done goofed somewhere. You probably moved the variable somewhere where it should have been moved. Maybe you wrote the ideal gas law down wrong. Luckily, the units are going to be in the back of the exam for you, so you should not write this down incorrectly. Make sure you use the right constant, because both of them are going to be there for you. Okay. That was simple 5. Simple 6. The valve between a 3-liter tank containing oxygen gas at 7.36 atmospheres and a 2.1-liter tank containing neon at 5.08 atmospheres is open. Calculate the ratio of partial pressures of O2 to neon in the container. This is going to be a Dalton's law question. So we're doing partial pressures. So we have a 3-liter container and a 2.1 container, and they're connected, and there's a valve, and the valve keeps the gases from meeting each other. You open that valve, so now you have a new volume. So the oxygen is going from a 3-liter container to a container that is both 3 plus 2.1. So the first thing we want to do for this one is we want to calculate the new volume for this container. So the new volume for this container is going to be 3 liters plus 2.10. It's going to be 5.10 liters. And we're going to use that value for our calculations. So we're going to assume that our temperature and our moles are constant. So it's going to be another Boyle's law. So let's do the pressure, the new pressure of oxygen when we open up the valve. New O2 pressure. Let's just do capital P. So we're going to have P1 V1 equals P2 V2, where P1 is going to be the pressure of oxygen initially, V1 is going to be the pressure of the gas in its initial container, P2 is what we're looking for, and V2 is the new volume. You'll notice this equation is very, very similar to your molarity dilutions, where you have M1 V1 equals M2 V2. So you can think of it exactly the same way, except you're not dealing with liquids, you're dealing with gases. So the original pressure of our oxygen is 7.36 atmospheres. Our initial volume was 3 liters. P2 is our variable, and our V2 is going to be our new volume, which was 5.10 liters. So I'm going to divide both sides by 5.10 to get this P2 so that we're solving for it on its own. So let's just do that here instead of writing another line. Okay. P2 is equivalent to 4.33 atmospheres. Right. So this is the pressure for oxygen. Now we're going to do exactly the same thing for neon. And I think I'm going to move to another clean sheet because I don't want to write over this. It's going to be really hard to see. I'm going to set this aside. We're going to come back to this number. We're going to need this number later. Set this aside so I have it later. Neon pressure. So again, P1, B1 equals P2, B2. The initial pressure of our neon was 5.08. Our initial volume was 2.10. P2s are our variables, what we're solving for. Our new volume was 5.10 liters. So again, I'm going to move the 5.10 to this side. So just put a marker all over my fingers. No. So bad. 5.10. Divided by 5.10 liters. P2 is going to be equal to 2.09 atmospheres. So this was, let's write down the numbers that we just saw for. The pressure of O2 was 4.33 atmospheres. The pressure of neon is 2.09. So now what we're going to do is we're going to calculate, the question was asking calculate the ratio of the partial pressures of O2 to neon. So we have to determine the partial pressures of each of these gases in this new container. So we're going to do the partial pressure of O2 first. Partial of O2. And that's going to be equal to the pressure of O2 on its own, which is 4.33 atmospheres, over the pressure total of the container. So the total pressure of the containers. This is going to be 4.33 atmospheres plus 2.09. When you do partial pressures, your units cancel out. What you're left with is literally just a number. It's a fractional number. This is going to give us a partial pressure of 0.674. So that was for O2. We're going to do the same thing for neon. Partial for neon. That's going to be equal to, again, the pressure of neon on its own, which is 2.09. Over the total pressure, 4.33 atmospheres plus 2.09 atmospheres. That's going to give us a partial pressure of 0.326. Now that we have our two partial pressures, all we have to do is do the ratio of, the question wants to know O2 to neon, so it's going to be the partial pressure of O2 in the numerator over, switch this up, partial pressure of neon. So it's going to be 0.674 over 0.326. That's going to give us 2.07. This is the ratio value of O2 to neon. So we had to walk through a couple steps for this one. We had to determine a new volume for the container. We had to determine the new pressure for each gas inside a new container. And then once we had our pressures of the new gases in the new container, we had to determine the partial pressures by doing Dalton's law of partial pressures, and then just doing the ratio of these two values, and that gives you the final answer. Okay. That's that. That was example number 6. Move on to, this is a kinetics, theory of kinetics for gases. So that we actually went over this example in class. We're just going to do it again. So for those who were a little bit confused, we can do it one more time. We're going to do a simplification that makes it a little bit easier. So in class, when I did this example, I determined the molecular mass for each gas, and then I plugged all of that into the average speed, and we got 4 numbers out of it. One for helium, helium, chlorine, and methane. Sorry, the question is 4 identical 1 liter flasks contain the gases helium, chlorine, methane, and ammonia, each at 0 degrees Celsius and at 1 atmosphere pressure. We have 3 questions. For which gas do the molecules have the highest average velocity? For which gas are the collisions elastic, and which gas has the lowest kinetic energy? So we're going to do this first one. That's the one that we did in class, where we worked out the molecular mass for all of them, and we found the speed for all of them. And so